"48 years ago," the universe whispered. A single radio signal, lasting 72 seconds, pierced the cosmic silence from the direction of Sagittarius. Then, nothing. Now, from that exact same patch of sky, something is hurtling toward us through the darkness. 3I Atlas, an interstellar visitor with chemistry that defies explanation and timing that stretches coincidence beyond belief. Like cosmic breadcrumbs leading to an answer we're afraid to find, these two mysteries share more than just a celestial return address. Stay with us as we unravel whether humanity has stumbled upon the greatest coincidence in astronomical history, or our first genuine contact with intelligence beyond Earth. Part 1. The Coincidence. Two mysteries, one constellation, 48 years apart. In 1977, a radio telescope in Ohio captured something that shouldn't exist, a signal so powerful, so precisely engineered that astronomer Jerry Eamon scrawled, "Wow," across the printout in red ink. The signal came from Sagittarius, pointing toward the crowded heart of our galaxy. It lasted exactly 72 seconds, then vanished forever. Now, in 2025, another visitor has arrived from that same patch of sky. This time, it's not invisible radio waves dancing across a computer screen. It's something tangible, something real, a mysterious object hurtling through space on a trajectory that screams, "I don't belong here." They call it 3I Atlas, the third confirmed interstellar visitor to grace our solar system. And like that radio whisper from decades past, it's approaching from Sagittarius. Is this mere coincidence? In a universe containing 2 trillion galaxies, each hosting hundreds of billions of stars, what are the odds that two of the most perplexing anomalies in modern astronomy would share the same celestial return address? Sagittarius isn't just another constellation decorating our night sky. When we gaze toward those familiar star patterns, we're looking directly into the gravitational maelstrom at the center of the Milky Way, home to Sagittarius A star, a supermassive black hole 4.3 million times the mass of our Sunday. It's astronomy's equivalent of Times Square, crowded, energetic, and perpetually active. Radio waves flood this region like urban noise, making it both the most obvious place to search for cosmic signals and the most challenging place to distinguish genuine messages from natural static. This cosmic coincidence becomes even more intriguing when you consider the frequency of that original wow signal. At 1420 MHz, it fell within what SETI researchers call the water hole, a relatively quiet band of the radio spectrum bracketed by emissions from hydrogen and hydroxyl molecules. For decades, scientists have argued this represents the universe's natural meeting place for interstellar communication. It's like a cosmic phone number that any technologically advanced civilization would instinctively know to dial. The hydrogen line itself holds special significance. At 1420.4 MHz, neutral hydrogen atoms undergo a quantum transition that every radio-literate species in the galaxy would recognize. It's written into the fundamental physics of the universe, a universal constant that transcends culture, biology, or technological development. If you wanted to send a message that would be understood across interstellar distances, this is exactly the frequency you'd choose. But here's where our story takes an unexpected turn. 3I Atlas was discovered on July 1, 2025, by the Atlas survey system operating from Chile's Atacama Desert. Unlike the billions of rocks orbiting peacefully within our solar system's gravitational embrace, this object is moving on what astronomers call a hyperbolic trajectory, meaning it's not bound to our sun at all. It came from somewhere else entirely, sailing through the cosmic void between star systems before our gravity briefly bent its path toward the inner solar system. The numbers don't lie. Its orbital eccentricity exceeds one by a significant margin, the mathematical signature of an interstellar wanderer. This isn't some asteroid that wandered too far from the belt or a comet shaken loose from the Oort cloud. 3I Atlas is a genuine visitor from beyond, carrying chemistry and secrets forged around an alien star. What makes this visitor particularly tantalizing is our unprecedented opportunity to study it. When Oumuamua, our first confirmed interstellar guest, swept through the system in 2017, we barely had time to point our telescopes before it disappeared back into the darkness. Comet Borisov in 2019 gave us a slightly longer window, but still departed before we could conduct truly comprehensive observations. 3I Atlas is different. Its trajectory grants us months of detailed observation, allowing the full arsenal of modern astronomy to bear witness. The James Webb Space Telescope is already capturing infrared spectra. Hubble is constraining its size and rotation. Ground-based observatories around the world are tracking its evolving coma and tail as solar radiation awakens dormant volatiles within its nucleus. We're witnessing something historically unprecedented, the chance to perform an autopsy on matter from another star system, to analyze the chemical fingerprints of worlds we may never directly observe. But that's not what makes this story truly extraordinary. What elevates 3I Atlas from fascinating to potentially revolutionary are the anomalies beginning to emerge from our observations. Early spectroscopic data reveals an unusually high ratio of carbon dioxide to water vapor, roughly 8:1 according to some measurements. Most comets from our own solar system show the opposite preference. Then there's the peculiar detection of nickel emission lines without corresponding iron signatures, defying our understanding of how these elements typically appear together in cometary atmosphere. The object's small size, Hubble measurements suggest an upper limit of just 5.6 kilometers across, possibly much smaller, combined with its impressive activity level, creates what some astronomers describe as an overperforming comet. It's producing more dust and gas than objects of similar size typically manage, as if operating by different rules entirely. Now, before we venture too far down speculative paths, we must acknowledge the extraordinary standards required for extraordinary claims. The history of astronomy is littered with anomalies that seemed alien until better data revealed perfectly natural explanations. Pulsars were once considered potential alien beacons. Fast radio bursts triggered similar speculation until we understood their cosmic origins. But what if this time is different? What if the coincidence of two unexplained phenomena originating from the same region of sky represents something more than statistical noise? What if 48 years ago we received a message and now we're witnessing its follow-up? This documentary will explore these questions without losing sight of scientific rigor. We'll examine the data with clear eyes, distinguish between measurement and speculation, and let the evidence guide our conclusions rather than our hopes. We'll trace the history of both mysteries, explore the latest scientific analyses, and consider possibilities that range from the mundane to the transformative. The wow, Signal, and 3I Atlas may ultimately prove unconnected, two separate mysteries united only by the human tendency to find patterns in randomness. But their convergence offers us something equally valuable, a lens through which to examine our place in a universe that continues to surprise us, humble us, and remind us how little we truly know about the cosmic neighborhood we call home. As 3I Atlas continues its journey through our solar system, approaching Mars in early October before rounding the Sun and beginning its long voyage back to interstellar space, we have a unique opportunity to listen, to watch, and to wonder. Because in a universe where two mysteries from the same patch of sky find their way to our cosmic doorstep, anything becomes possible. Part 2. The Night of the Wow. Signal. August 15th, 1977. While most of America slept, a radio telescope in Ohio was performing its nightly vigil, slowly scanning the heavens for whispers of intelligence among the stars. The Big Ear radio telescope wasn't much to look at, essentially a massive metal trough carved into the Ohio countryside, stretching the length of 3 football fields. Unlike the iconic dish antennas we typically picture, Big Ear used a fixed reflector design that relied on Earth's rotation to sweep its beam across the sky. This meant astronomers couldn't quickly retarget interesting sources. They got one 72-second look at each patch of sky per day, then had to wait 24 hours for another chance. On this particular night, as the constellation Sagittarius drifted through the telescope's field of view, something extraordinary happened. The receivers registered a signal unlike anything in their databases, a narrow-band transmission centered at 1420.455 MHz, climbing steadily in intensity before fading away exactly as expected for an astronomical source tracked by the telescope's beam. But here's what made it remarkable. The signal was strong, incredibly strong. Recent reanalyses suggest peak intensity may have reached 250 Janskis, roughly 30 times brighter than typical background noise. In the radio astronomy world, that's not a whisper. That's a shout. Days later, volunteer astronomer Jerry Eman was reviewing the computer printouts from that night's observations. The Big Ear's primitive computers converted radio intensity into alphanumeric characters, with higher numbers and letters representing stronger signals. As Eamon's eyes scanned the rows of ones and twos representing cosmic silence, they stopped at something impossible. 6 EQ UJ 5. The sequence climbed and fell in perfect symmetry, exactly matching the expected profile of a point source tracked by the telescope's beam. Eamon grabbed a red pen and circled the anomalous data. In the margin, he scrawled a single word that would echo through decades of SETI research. Wow. The signal's characteristics read like a textbook example of what SETI researchers had long theorized they might find. It was narrow-band, suggesting an artificial origin. Nature rarely produces such precisely defined frequencies. It appeared to originate from a fixed point in space, rather than moving like a satellite. Most intriguingly, it fell almost exactly on the hydrogen line frequency, the 21-centimeter transition that many scientists had identified as a logical choice for interstellar communication. Big Ear's unique design included two separate beam feeds positioned side by side, allowing it to observe two adjacent patches of sky simultaneously. When a cosmic source moved through the telescope's view, it should trigger both beams in sequence, about 3 minutes apart. The wow signal appeared in only one beam, creating an ambiguity about its exact position that would plague follow-up efforts for decades. The Ohio State University team immediately recognized the signal's significance. Within days, they had repositioned other telescopes toward the suspected source region and begun intensive searches. They found nothing. The signal had vanished as mysteriously as it had appeared, leaving behind only that single printout and a growing sense that they had witnessed something unprecedented. This began what would become one of the most extensive follow-up campaigns in SETI history. Over the following years, dozens of radio telescopes around the world would point toward the WOW signal's suspected location. The Very Large Array, Arecibo, Parkes, and countless others joined the hunt. Some searched continuously, others intermittently. All came up empty. The signal's non-repeating nature presented SETI researchers with a fundamental challenge. How do you verify something that happened once and never again? How do you distinguish between a genuine extraterrestrial message and an unknown natural phenomenon or unidentified interference? The WOW signal became a perfect example of what philosophers call the problem of induction, drawing general conclusions from specific observations. As years turned to decades, various explanations emerged to account for the signal's mysterious properties. Some researchers suggested it might represent a previously unknown class of astronomical object, perhaps a neutron star undergoing a rare magnetic field reconfiguration, or a hydrogen cloud illuminated by some distant energetic event. Others proposed more exotic scenarios involving collapsed stars, black holes, or interstellar mazes triggered by cosmic collisions. One particularly contentious explanation emerged in 2012 when Antonio Paris suggested the signal might have originated from comets carrying hydrogen clouds. The hydrogen, when illuminated by solar radiation, could theoretically produce emissions at the hydrogen line frequency. Paris identified two comets, 266P Christensen and 335P Gibbs, that would have been in roughly the right position in 1977. The SETI community's response was swift and largely negative. Big Ear veterans pointed out that comets moved noticeably across the sky, while the WOW signal appeared stationary. The hydrogen cloud hypothesis also failed to account for the signal's extraordinary intensity and narrow bandwidth. More fundamentally, no similar emissions had ever been detected from the hundreds of other comets observed by radio telescopes over the decades. This controversy highlighted a crucial aspect of SETI research: the burden of proof. For a signal to be considered genuinely extraterrestrial, it must not only lack conventional explanations, but also demonstrate characteristics that strongly suggest intelligence. The WOW signal met the first criterion but struggled with the second. It was anomalous, yes, but anomalous in ways that could potentially be explained by unknown natural phenomena. Recent reanalysis has shed new light on the signal's properties. In 2024 and 2025, researchers used improved data processing techniques to extract additional information from the original Big Ear archives. They narrowed the signal's possible location, confirmed its extraordinary intensity, and ruled out several classes of terrestrial interference. Most significantly, they identified patterns in surrounding data that might support a natural maser explanation: hydrogen gas amplifying radio waves in response to some distant energetic event. This maser hypothesis has gained considerable support among SETI researchers. Masers occur naturally in space when molecules become excited by nearby energy sources, creating conditions analogous to cosmic radio lasers. Hydrogen masers, while rare, have been observed in star-forming regions and around certain types of evolved stars. A transient hydrogen maser, triggered by a magnetar flare, supernova shockwave, or similar high-energy event, could potentially produce a signal matching the WOW characteristics. Yet even this seemingly natural explanation carries profound implications. If the WOW signal represented a hydrogen maser flare, it was unlike any previously observed. The precision of its frequency, the perfection of its temporal profile, and its occurrence at the exact wavelength that SETI researchers had long considered the most logical choice for interstellar communication stretches coincidence to its breaking point. The signal's legacy extends far beyond its specific characteristics. It demonstrated that Big Ear was capable of detecting powerful transmissions from interstellar distances. It validated SETI search strategies and inspired a generation of radio astronomers to take the possibility of extraterrestrial intelligence seriously. Most importantly, it established a standard for what constitutes credible evidence in SETI research, a standard that continues to influence how we evaluate anomalous signals today. As we'll see, this standard becomes particularly relevant when examining our current interstellar visitor, 3I Atlas, and the tantalizing possibility that its arrival might somehow connect to that famous signal from 4 decades ago. Part 3. The Hydrogen Line, the Universal Beacon. In the vast library of the electromagnetic spectrum, where every frequency tells a different cosmic story, one particular wavelength stands out as special, not just to human scientists, but potentially to any intelligent civilization that has ever gazed up at the stars and wondered if they were alone. At exactly 1420.40575 MHz, something remarkable happens in the quantum realm. Hydrogen atoms, the simplest and most abundant element in the universe, undergo what physicists call a spin-flip transition. It's an almost impossibly subtle event. The single electron orbiting a hydrogen nucleus occasionally flips its magnetic orientation relative to the proton, releasing a precise packet of energy in the form of radio waves. This transition takes an average of 11 million years to occur naturally in any given hydrogen atom. Yet across the cosmic expanses where hydrogen clouds stretch for light years, containing trillions upon trillions of atoms, this 21-centimeter radiation creates a constant, detectable hum. It's the universe's own background music, played on the most fundamental instrument imaginable, the building block of stars, planets, and life itself. What makes this frequency extraordinary isn't just its universality but its inevitability. Any civilization that discovers radio astronomy will find the hydrogen line. They'll measure its exact frequency, study its properties, and recognize its significance. Unlike cultural artifacts or biological characteristics that vary between worlds, the hydrogen line represents a universal constant, a cosmic landmark that transcends species, technology, or evolutionary path. This realization struck early SETI researchers like a revelation. Giuseppe Cocconi and Philip Morrison, in their groundbreaking 1959 paper that essentially founded modern SETI, identified the hydrogen line as nature's own interstellar hailing frequency. Their logic was elegant. If you wanted to send a message that would be understood by any radio-capable civilization, you'd use a frequency they would inevitably discover and monitor. The hydrogen line sits within what SETI pioneers came to call the water hole, a relatively quiet region of the radio spectrum bracketed by emissions from hydrogen at 1420 MHz and hydroxyl molecules around 1660 to 1670 MHz. Between these natural boundaries lies a band where cosmic radio noise drops to minimum levels, creating what Bernard Oliver of Hewlett-Packard famously called the closest thing to a universal quiet channel that we're likely to find. The poetic symbolism wasn't lost on researchers. Hydrogen and hydroxyl, H and OH, combine to form water, the molecule most essential to life as we know it. In a universe where countless civilizations might gather around their own versions of watering holes to share information and maintain social bonds, perhaps advanced species would naturally congregate around this cosmic water hole to exchange interstellar messages. But the hydrogen line's significance extends beyond mere symbolism. Its physical properties make it ideal for long-distance communication. The 21-centimeter wavelength passes easily through interstellar dust and gas that would block shorter wavelengths. It's naturally narrow band, allowing for efficient signal transmission with minimal energy requirements. Most importantly, it's protected from interference. Many countries have established radio quiet zones around 1420 MHz, specifically to preserve this frequency for astronomical research. When the WOW signal appeared at 1420.455 MHz, within just 50 kHz of the pure hydrogen line frequency, it seemed to validate decades of SETI theoretical work. Here was exactly the type of signal researchers had predicted they might find: narrow, band, powerful, and positioned at the universe's most logical calling card. Yet this apparent validation carried its own complications. The hydrogen line's natural occurrence means it's also a frequency where genuine astrophysical phenomena can masquerade as artificial signals. Hydrogen masers, cosmic radio lasers formed when interstellar gas becomes excited by nearby energy sources, can produce intense, narrow-band emissions exactly where SETI researchers are most actively listening. These masers occur in various cosmic environments. Star-forming regions often harbor hydrogen masers as protostars heat surrounding gas clouds. Supernova remnants can trigger maser activity as shockwaves propagate through interstellar medium. Even more exotic events, magnetar flares, gamma-ray bursts, or the tidal disruption of stars by supermassive black holes, might theoretically create the conditions necessary for transient hydrogen maser emission. This creates what SETI researchers call the natural mimicry problem. The very frequency we expect intelligent signals to use is also where nature can produce signals that appear intelligent. It's a cosmic version of crying wolf, where genuine technological signals must be distinguished from sophisticated natural phenomena that have learned to imitate them perfectly. Modern SETI searches have developed increasingly sophisticated techniques to address this challenge. They look for characteristics that would be difficult for natural sources to reproduce: complex modulation patterns, precise frequency drifts that compensate for relative motion, or structured information content that implies deliberate encoding. They seek repeatability, signals that appear multiple times from the same location, suggesting a persistent source rather than a one-time event. The waterhole concept has also evolved beyond its original hydrogen-hydroxyl boundaries. Some researchers now advocate for expanded waterholes that include other biologically relevant molecular transitions. The ammonia line at 23 GHz, various organic compounds, and even the cosmic microwave background's quiet windows have all been proposed as alternative meeting places for interstellar communication. Despite these complications, the hydrogen line retains its special status in SETI research. The ongoing Breakthrough Listen project dedicates significant observing time to hydrogen line frequencies. China's 500-meter aperture spherical telescope regularly monitors this band during its SETI observations. Even optical SETI searches sometimes use laser wavelengths that correspond to hydrogen transitions in the visible spectrum. The line's significance extends beyond signal detection to signal transmission as well. If humanity ever decides to announce our presence to the galaxy, many proposed transmission schemes involve the hydrogen line. Its universal recognition makes it an ideal carrier frequency for interstellar messages, ensuring that any recipients would immediately recognize the signal as artificial rather than natural. Recent technological advances have dramatically improved our ability to search hydrogen line frequencies with unprecedented sensitivity and resolution. Modern radio telescopes can distinguish signals separated by mere hertz across bandwidths spanning megahertz. They can detect polarization characteristics that might reveal the magnetic field configurations of distant sources. Most importantly, they can process data in real time, enabling immediate follow-up observations of transient signals rather than waiting days or weeks for post-processing to reveal anomalies. This technological revolution becomes particularly relevant as we consider 3I Atlas's journey through our solar system. If this interstellar visitor were somehow connected to the WOW signal, if both represent components of some vast interstellar communication effort, then the optimal time to search for repeat transmissions would be during the comet's closest approaches to major solar system bodies. The hydrogen line offers the perfect window for such searches. Its frequency is precisely defined, universally recognized, and carefully protected from interference. As 3I Atlas approaches Mars, rounds the Sun, and passes closest to Earth, radio telescopes worldwide will have the opportunity to listen at exactly the frequency where the original WOW signal appeared 4 decades ago. Whether they hear anything or not, the search itself represents something profound: humanity's continuing commitment to the possibility that we are not alone, and our willingness to listen for messages written in the universe's own fundamental language. Part 4. The Unrepeatable Mystery. In science, reproducibility is everything. Discoveries that can't be replicated are viewed with deep suspicion, relegated to the footnotes of history, until independent confirmation transforms skepticism into acceptance. The WOW signal has spent 48 years in this scientific purgatory, too significant to ignore, too isolated to embrace. The follow-up campaigns began almost immediately after Jerry Eamon's red pen immortalized that famous printout. Within weeks of the discovery, radio telescopes around the world were pointing toward the signal's suspected location in Sagittarius. The Big Ear team themselves conducted extensive searches, scanning the region repeatedly throughout the late 1970s and early 1980s. They found cosmic silence. The Very Large Array in New Mexico joined the hunt, bringing unprecedented resolution and sensitivity to bear on the mystery. Arecibo's massive dish, capable of detecting signals far weaker than Big Ear could register, swept the area methodically. The Parkes Observatory in Australia provided Southern Hemisphere coverage. International collaborations formed specifically to address the WOW enigma, pooling resources and observing time in an unprecedented effort to recapture lightning in a bottle. Decades passed. The searches continued, growing more sophisticated as technology advanced. Modern digital receivers replaced analog systems, offering better sensitivity and the ability to record vast amounts of spectral data for later analysis. Automated signal processing algorithms could identify narrow-band emissions that human observers might miss. Yet, despite exponential improvements in our detection capabilities, the WOW signal remained stubbornly unique. This failure to repeat became both the signal's greatest weakness and its most intriguing characteristic. natural astronomical sources typically display some form of periodicity or recurring activity. Pulsars pulse. Variable stars vary. Even the most exotic phenomena, gamma-ray bursts, fast radio bursts, or magnetar flares, tend to occur in patterns or from sources that produce multiple events. The WOW signal's splendid isolation challenged conventional astronomical wisdom. By the early 21st century, some researchers had begun to write off the signal as an instrumental artifact or unidentified interference. Perhaps the Big Ear's aging electronics had suffered a momentary malfunction. Maybe a passing aircraft had created unexpected reflections. Possibly even a microwave oven in nearby Delaware had somehow leaked radiation at exactly the right frequency and timing to create an apparent astronomical signal. But the 2024 and 2025 reanalyses changed everything. A team led by researchers from the National Radio Astronomy Observatory used advanced data processing techniques to extract new information from the original Big Ear archives. Their findings painted a picture of a signal even more extraordinary than originally thought. First, they narrowed the possible source location. By carefully analyzing the signal's intensity profile and the Big Ear's known beam characteristics, they constrained the origin to a region only about 8 arc-minutes across, roughly 1/4 the apparent diameter of the full moon. This precision ruled out many classes of terrestrial interference and suggested a genuine point source somewhere in interstellar space. Second, they confirmed the signal's remarkable intensity. Previous estimates had been conservative, but the new analysis suggested peak flux density may have exceeded 250 Janskis, making it one of the strongest radio signals ever detected from outside our solar system. For comparison, the Crab pulsar, one of the most powerful radio sources in our galaxy, appears roughly 50 times weaker when observed at similar frequencies. Most significantly, the reanalysis revealed subtle patterns in the surrounding data that had gone unnoticed for decades. Weak enhancements appeared at nearby frequencies and times, suggesting the main signal might have been embedded within a more complex emission structure. These patterns were tantalizingly consistent with what astronomers might expect from a hydrogen maser undergoing rapid temporal evolution. This maser hypothesis has emerged as the leading natural explanation for the WOW signal. Masers, cosmic radio lasers created when interstellar molecules become excited by nearby energy sources, can produce intense, narrowband emissions that closely mimic artificial signals. Hydrogen masers, while rare, have been observed in star-forming regions and around evolved stars undergoing mass loss. The scenario requires specific conditions. A cloud of hydrogen gas must be illuminated by some powerful energy source, perhaps a magnetar flare, supernova shockwave, or gamma-ray burst from a distant galaxy. The radiation excites hydrogen atoms throughout the cloud, creating population inversions that amplify radio waves at the 21 centimeter frequency. As the energy pulse propagates through the cloud, different regions light up in sequence, creating a transient maser that might last minutes to hours before fading away forever. This explanation accounts for several puzzling aspects of the WOW signal. It explains the precise frequency match to the hydrogen line. It predicts the narrow bandwidth observed in the signal. It allows for the extraordinary intensity through maser amplification. Most importantly, it explains why the signal never repeated. The triggering event was presumably a one-time occurrence that created temporary conditions unlikely to be duplicated. Yet even this natural explanation carries profound implications. If the WOW signal was indeed a hydrogen maser, it represents a type of astrophysical event that has never been observed before or since. The timing would be remarkable, occurring at exactly the frequency where humans were conducting their most intensive SETI searches. The location would be significant, originating from the same region of sky that has now produced our most mysterious interstellar visitor. Some researchers argue that the Mesa hypothesis, while more plausible than extraterrestrial intelligence, still stretches coincidence to uncomfortable limits. They point out that hydrogen masers powerful enough to produce the observed signal intensity would require energy inputs comparable to stellar explosions. Such events should be detectable across multiple wavelengths, yet no corresponding X-ray bursts, gamma-ray flares, or optical transients were recorded from the WOW signal's direction around August 1977. The debate highlights a fundamental challenge in SETI research: the difficulty of distinguishing between unknown natural phenomena and potential artificial signals. As our understanding of cosmic environments expands, we discover that nature is capable of producing signals that appear increasingly sophisticated. Pulsars, when first detected, seemed so precisely timed that astronomers half-jokingly labeled them "little green men." Fast radio bursts displayed such exotic characteristics that some researchers initially suspected technological origins. The WOW signal sits at the intersection of known and unknown, natural and artificial, possible and impossible. Its failure to repeat doesn't prove it wasn't extraterrestrial. An alien civilization might have transmitted a single message before their star exploded, their planet was destroyed, or they simply moved on to other target systems. Conversely, its occurrence at the hydrogen line frequency doesn't prove it was artificial. Nature has shown remarkable creativity in mimicking the signals we expect to find. What we're left with is uncertainty, the kind of productive uncertainty that drives scientific progress. The WOW signal forced astronomers to develop better search strategies, more sensitive instruments, and more sophisticated analysis techniques. It demonstrated that our radio telescopes were capable of detecting powerful signals from interstellar distances. Most importantly, it established benchmarks for what constitutes credible evidence in SETI research. These benchmarks become crucial as we examine 3I Atlas and consider the tantalizing possibility that its arrival might somehow connect to that famous signal from 4 decades ago. Unlike radio waves that leave no physical trace, our interstellar visitor offers the opportunity for direct, repeatable observations. We can measure its chemistry, track its trajectory, and search for any signals it might be transmitting as it journeys through our solar system. The question that haunts every SETI researcher remains: are we looking at 2 separate mysteries, or 2 components of something larger? Part 5. Why Sagittarius Matters. When ancient astronomers looked toward the constellation Sagittarius, they saw a centaur archer drawing his bow toward the heart of the Milky Way. They couldn't have known they were gazing into the most extraordinary cosmic neighborhood in our galaxy, a region so dense with stars, so rich in exotic phenomena, that it reads like a science fiction writer's fever dream made manifest. Sagittarius occupies a unique position in our night sky. Unlike most constellations, which appear to us as random star patterns projected onto the celestial sphere, Sagittarius marks a genuine cosmic landmark. When we look toward those familiar stellar shapes, we're peering directly into the galactic center, the gravitational and energetic heart of the Milky Way galaxy itself. 26,000 light-years away, hidden behind vast clouds of interstellar dust, lies one of the universe's most extreme objects, Sagittarius A star, a supermassive black hole containing 4.3 million times the mass of our Sunday. This gravitational monster anchors our entire galaxy, holding hundreds of billions of stars in orbital dance while periodically devouring matter that ventures too close to its event horizon. The region surrounding Sagittarius A star defies easy description. Star densities reach levels almost incomprehensible to residents of our galaxy's sleepy suburban spiral arm. Near the galactic center, stars pack together so tightly that planetary systems would be constantly disrupted by gravitational perturbations. Radiation levels spike to intensities that would sterilize worlds. Magnetic fields twist and snap with energies that dwarf anything in our local cosmic neighborhood. This cosmic chaos generates a radio astronomer's paradise and nightmare. The galactic center region produces more radio emission than any other direction in our sky. When Carl Jansky first detected radio waves from space in 1932, accidentally founding the field of radio astronomy, the strongest signal came from the direction of Sagittarius. Every class of radio source known to astronomy can be found in abundance along this sightline: pulsars, supernova remnants, stellar nurseries, planetary nebulae, and exotic phenomena that still challenge our understanding. For SETI researchers, this abundance creates both opportunity and obstacle. On one hand, if an advanced civilization wanted to establish a galactic communications hub, the dense stellar populations around the galactic center might provide an ideal location. Thousands of star systems cluster within regions smaller than the distance from Earth to our nearest stellar neighbors. Any broadcast from this region could potentially reach vast numbers of worlds simultaneously. On the other hand, the natural radio noise from galactic center phenomena makes signal detection extraordinarily challenging. It's like trying to hear a whispered conversation in the middle of a bustling city center. Genuine artificial signals must compete with emissions from countless natural sources, creating a cosmic version of the cocktail party problem. How do you focus on one voice when everyone is talking at once? The wow signal appeared against this noisy backdrop, which makes its characteristics even more remarkable. Despite originating from one of the most radioactive regions of our galaxy, it managed to stand out clearly against the background. Its narrow bandwidth and precise frequency suggested a source capable of producing highly focused emissions, exactly what you might expect from either an artificial transmitter or an unusually coherent natural phenomenon like a maser. The scale of Sagittarius as a constellation spans roughly 30 degrees across the sky, equivalent to 60 full moons arranged side by side. This means that saying both the WOW signal and 3I Atlas originate from Sagittarius encompasses a vast range of possible directions and distances. The apparent coincidence might be less meaningful than it initially appears, particularly given that Sagittarius covers some of the most active radio regions of our galaxy. Yet even accounting for this vast angular scale, the directional correlation between our two mysteries remains intriguing. The WOW signal's position, recently narrowed to within 8 arcminutes, places it in the same general region of Sagittarius from which 3I Atlas appears to approach. While this could certainly represent pure coincidence, it's the kind of coincidence that makes astronomers take notice. The physics of interstellar space adds another layer of complexity to our story. Objects approaching our solar system from the direction of Sagittarius have traveled through some of the most extreme environments in our galactic neighborhood. They've navigated gravitational fields distorted by massive star clusters, radiation environments that would rapidly alter surface chemistry, and magnetic fields that could potentially affect the trajectories of charged particles or even magnetically susceptible objects. 3I Atlas, if it indeed originated from somewhere along the Sagittarius sightline, has survived this cosmic obstacle course while retaining characteristics that distinguish it from typical solar system comets. Its unusual chemistry, particularly the high carbon dioxide to water ratio and the detection of nickel without corresponding iron signatures, might reflect formation conditions around a different type of star or exposure to galactic environments unlike anything experienced by objects native to our solar system. The constellation's significance extends beyond mere direction to encompass questions of cosmic demographics and communication strategy. If advanced civilizations exist in our galaxy, they're most likely to emerge around long-lived, stable stars in regions with sufficient heavy element abundances to support planet formation and chemical evolution. The galactic center region, despite its harsh radiation environment, contains some of the oldest and most metal-rich star systems in the Milky Way. From a strategic communication perspective, the galactic center offers an ideal broadcast location for civilizations wanting to reach the maximum number of potential recipients. A powerful radio beacon placed anywhere in the galactic bulge could be detected across vast swaths of the galaxy's disk, reaching thousands of star systems simultaneously. It's the cosmic equivalent of putting your radio station on the highest mountain peak. This strategic advantage might explain SETI's historical focus on the galactic center region and the hydrogen line frequency. Early SETI pioneers reasoned that if they were going to establish an interstellar communication network, they would place it where it could reach the most participants with the least energy expenditure. The waterhole frequencies offer the clearest channel, and the galactic center provides the optimal broadcast location. Modern astronomical surveys are beginning to reveal the true extent of interstellar traffic through our solar system. The Legacy Survey of Space and Time, set to begin operations later this decade, will likely discover hundreds or thousands of additional interstellar objects, transforming our current sample of 3 visitors into a statistical population. Most of these future discoveries will likely come from random directions, reflecting the chaotic motions of objects ejected from distant planetary systems over billions of years. If 3I Atlas proves to be genuinely unusual, if its chemistry, behavior, or associated phenomena distinguish it from the population of natural interstellar wanderers, then its arrival from the Sagittarius direction gains additional significance. Random chance becomes less likely as an explanation when multiple anomalies cluster in both space and time. The constellation Sagittarius has given us 2 of astronomy's most enduring mysteries: a radio signal that appeared once and vanished forever, and a visitor from interstellar space displaying characteristics that challenge our understanding of cometary physics. Whether these represent genuine connections or mere coincidence, they share a common thread. They force us to confront the possibility that our cosmic neighborhood might be more active, more populated, and more connected than we ever imagined. As 3I Atlas continues its journey toward the inner solar system, approaching first Mars and then the Sun itself, we have an unprecedented opportunity to search for any radio emissions that might emanate from its vicinity. If something begins transmitting on 1420 MHz as this interstellar wanderer passes through our planetary neighborhood, the coincidence would become impossible to ignore. But even if our searches detect only silence, the journey itself teaches us something valuable about the universe we inhabit and our place within it. Sagittarius has shown us that the cosmos is full of mysteries waiting to be discovered, phenomena that stretch our understanding and humble our certainty about what's possible in the vast darkness between the stars. Part 6. The Arrival of 3I Atlas. July 1st, 2025. While most of the world slept, an automated telescope system in Chile's Atacama Desert was methodically photographing the night sky, searching for asteroids that might pose threats to Earth. The Atlas Survey, short for Asteroid Terrestrial Impact Last Alert System, had been conducting this vigil for years, cataloguing the movements of countless rocks orbiting peacefully within our solar system's gravitational embrace. But on this particular night, the cameras captured something extraordinary. Moving against the background, stars at a speed that immediately caught the attention of automated detection algorithms, was an object that clearly didn't belong to our solar system family. Its trajectory screamed outsider, a hyperbolic path that curved around our sun, not because it was gravitationally bound, but because it was merely a temporary visitor, bent briefly from its original course before continuing into the darkness between stars. The Discovery team, led by Atlas Principal Investigator John Tonry, quickly recognized they had found something historically significant. Preliminary orbital calculations revealed an eccentricity exceeding 1.0, the mathematical signature of an interstellar wanderer. This wasn't some asteroid that had wandered too far from the belt or a long-period comet returning from the Oort cloud. Object 3I Atlas, as it would soon be designated, was genuinely alien to our solar system. Within hours, observatories around the world were training their instruments on this cosmic interloper. The race was on to gather as much data as possible before the object's trajectory carried it beyond the reach of our most powerful telescopes. Unlike Oumuamua, which had been discovered after its closest approach to the Sun and was already racing back toward interstellar space, 3I Atlas was still inbound, offering months of detailed observation opportunities. Early observations revealed an object unlike anything in our cosmic neighborhood. As 3I Atlas approached the inner solar system, solar radiation began awakening volatile compounds frozen within its nucleus. a ghostly coma of gas and dust began materializing around the object, followed soon after by the development of a distinct tail, classic signatures of cometary activity. But this was no ordinary comet. Spectroscopic analysis revealed chemistry that defied expectations based on objects native to our solar system. The James Webb Space Telescope, humanity's most powerful infrared observatory, detected unusually high concentrations of carbon dioxide relative to water vapor, a ratio roughly 8:1 according to early measurements. Most comets from our own system show the opposite preference, with water dominating their volatile inventories. The Hubble Space Telescope contributed crucial size constraints through high-resolution imaging. Its observations placed an upper limit of approximately 5.6 kilometers on the nucleus diameter, with some analyses suggesting the object might be significantly smaller, perhaps as compact as 320 meters across. For a body producing such impressive cometary activity, this represented what astronomers euphemistically called overperformance. Ground-based observatories added their own pieces to the puzzle. The Gemini South Observatory in Chile captured stunning images of the growing coma and tail, documenting their evolution as 3I Atlas drew closer to the Sunday. The Very Large Telescope in Chile's Atacama Desert conducted detailed spectroscopic surveys, revealing the presence of nickel emission lines, a common feature in many comets, but with an unusual twist. Typically, when astronomers detect nickel in cometary atmospheres, they also find corresponding signatures of iron. These elements often occur together in cosmic environments, having similar chemical properties and formation histories. But 3I Atlas appeared to be outgassing substantial quantities of nickel while showing little to no detectable iron, an unusual characteristic that sparked considerable debate among cometary scientists. The object's orbital characteristics added to its mystique. 3I Atlas was approaching on what astronomers call a retrograde trajectory, meaning it orbited the Sun in the opposite direction from planets and most other solar system objects. Its orbital inclination of approximately 5 degrees relative to the ecliptic plane meant it was moving roughly within the same geometric plane as the planets, but against their direction of motion, like a car driving the wrong way on a highway. As summer progressed into autumn, 3I Atlas continued brightening as solar heating increased its activity level. By late August, the object was producing what observers described as vigorous water emission, creating an expanding atmosphere of gas and dust that grew more prominent with each passing week. Imaging campaigns documented the tail's evolution, showing how solar radiation pressure gradually pushed ejected material into the characteristic curved pattern that has fascinated humanity since ancient times. The object's brightness remained frustratingly modest for casual observers. Peak apparent magnitude was expected to reach only 11 to 13, far too faint for naked eye visibility and requiring substantial telescopes for detailed observation. This meant that unlike famous comets such as Hale-Bopp or Hyakutake, 3I Atlas would remain a specialist's object, visible primarily to professional astronomers and dedicated amateurs with serious equipment. Safety considerations dominated public discussions once news of the discovery spread. NASA and other space agencies quickly calculated the object's future trajectory, confirming that 3I Atlas posed no threat to Earth at any point during its passage through our solar system. Its closest approach to our planet would occur on December 19, 2025, at a comfortable distance of approximately 270 million kilometers, roughly twice the distance from Earth to the Sunday. The discovery represented something historically unprecedented, the third confirmed interstellar object detected passing through our solar system. The first, 1I Oumuamua, had swept through in 2017, leaving behind more questions than answers about its unusual elongated shape and mysterious non-gravitational acceleration. The second, 2I Borisov, arrived in 2019 as a more conventional comet, but still offered tantalizing glimpses of chemistry forged around an alien star. 3I Atlas promised to be different. Its inbound trajectory provided months of observation time, allowing the full arsenal of modern astronomy to study an authentic sample of matter from another star system. Every spectrum, every image, every measurement would contribute to our understanding of planetary system formation beyond our own cosmic neighborhood. But perhaps most intriguingly, 3I Atlas was approaching from the same general direction as that famous radio signal from 4 decades earlier. Both the WOW transmission and our interstellar visitor pointed back toward Sagittarius, toward the crowded heart of our galaxy, where stars pack together in densities unimaginable in our local cosmic suburb. The coincidence was impossible to ignore, even as scientists emphasized the vast angular scale that, from Sagittarius, encompassed. Yet as professional observatories began their intensive monitoring campaigns and citizen scientists around the world pointed their telescopes toward this cosmic wanderer, a question lingered in the background of every observation session. Was 3I Atlas simply another natural remnant of planetary system formation, ejected eons ago from some distant star and now passing randomly through our solar system? Or might its arrival somehow connect to that mysterious radio whisper that had tantalized SETI researchers for nearly half a century? The answer, if it existed, would have to wait for the data. Part 7. Signs of the Unnatural. As observations of 3I Atlas accumulated throughout the summer of 2025, a picture emerged that challenged conventional expectations about what interstellar comets should look like. Each new spectrum, every high-resolution image, and every photometric measurement added another piece to a puzzle that seemed designed to perplex astronomers. The most striking anomaly appeared in the object's chemical composition. When the James Webb Space Telescope turned its unprecedented infrared vision toward 3I Atlas, it revealed a cometary atmosphere dominated by carbon dioxide in concentrations that defied explanation. Most comets native to our solar system exhibit the opposite pattern. Water vapor typically outshines carbon dioxide by factors of 10 or more. But 3I Atlas displayed a carbon dioxide to water ratio of approximately 8:1, suggesting formation conditions radically different from anything in our cosmic neighborhood. This chemical inversion carried profound implications for our understanding of planetary system formation. In our solar system, comets represent frozen archives of the primordial materials that condensed in the outer regions of the solar nebula 4.6 billion years ago. Their compositions reflect the temperature and pressure conditions that existed when the Sun was still a young star surrounded by a disk of gas and dust. Finding a comet with dramatically different chemistry implied formation around a star with different properties, perhaps hotter, more massive, or enriched with different abundances of heavy elements. But carbon dioxide dominance wasn't the only puzzle. As 3I Atlas continued its approach toward the inner solar system, it began displaying what observers cautiously termed overperformance. The Hubble Space Telescope's size measurements suggested a nucleus no larger than 5.6 kilometers across, with some analyses indicating the object might be significantly smaller, potentially compact enough to fit within the boundaries of a typical city. Yet, despite its modest dimensions, 3I Atlas was producing cometary activity comparable to objects many times its size. The coma, the ghostly atmosphere of gas and dust surrounding the nucleus, expanded to hundreds of thousands of kilometers in diameter. The tail stretched millions of kilometers behind the object, creating a spectacular display visible to ground-based telescopes despite the comet's overall faintness. This apparent overperformance sparked intense debate among cometary physicists. Small bodies typically struggle to maintain the kind of vigorous outgassing observed in 3I Atlas because they have less surface area to absorb solar radiation and fewer internal volatiles to sublimate into space. The object seemed to be operating by different rules, as if its compact nucleus contained unusually reactive materials or possessed an internal structure optimized for maximum volatile release. Spectroscopic observations added another layer of mystery. When the Very Large Telescope in Chile analyzed the light emitted by 3I Atlas's coma, it detected strong emission lines from nickel atoms, a common finding in many comets that typically indicates the presence of metallic particles being vaporized by solar radiation. But conspicuously absent were corresponding emission lines from iron, nickel's frequent companion in cosmic environments. This selective metal emission puzzled astronomers familiar with the typical chemistry of solar system comets. Nickel and iron share similar chemical properties and often occur together in the same mineral phases. When cometary nuclei heat up and begin outgassing, both elements typically appear in the resulting spectra with predictable abundance ratios. 3I Atlas seemed to be violating this expectation, somehow producing substantial nickel emission while maintaining iron concentrations below detection limits. Various explanations emerged to account for this unusual metal signature. Some researchers suggested that 3I Atlas might contain iron bound in chemical compounds that require higher temperatures to volatilize, meaning iron emission might appear later as the comet approached closer to the sunday. Others proposed that the object's formation environment might have favored nickel-rich over iron-rich minerals, creating intrinsic abundance differences that persisted across interstellar distances. The object's orbital characteristics contributed additional intrigue to the growing list of anomalies. 3I Atlas was approaching on a retrograde trajectory, moving in the opposite direction from most solar system objects, with an orbital inclination of only about 5 degrees relative to the ecliptic plane. This meant it was traveling roughly within the same geometric plane as the planets, but against their direction of motion. While retrograde motion isn't impossible for natural objects, it's statistically uncommon. Most materials ejected from other planetary systems would be expected to approach from random directions with randomly oriented orbital planes. Finding an interstellar visitor moving retrograde but nearly coplanar with our solar system represented an additional coincidence in an already coincidence-rich discovery. As 3I Atlas continued brightening throughout late summer, reaching peak activity levels well beyond 3 astronomical units from the Sun, some observers began noting its unusually early onset of cometary behavior. Most objects from our solar system's outer regions remain dormant until they approach much closer to our star. The fact that 3I Atlas was already producing substantial coma and tail activity at such large distances suggested either unusual volatile composition or enhanced sensitivity to solar heating. These accumulating anomalies inevitably attracted attention from researchers who specialize in identifying potentially artificial objects. R.V. Loeb of Harvard University, who had previously argued that Oumuamua might represent alien technology based on its unusual acceleration and extreme elongation, began analyzing the available data on 3I Atlas for signs of non-natural origin. Loeb's preliminary assessments focused on the object's apparent overperformance and unusual chemistry as potential technosignatures, characteristics that might indicate artificial rather than natural origin. He noted that the carbon dioxide dominance could theoretically result from industrial processes rather than primordial condensation, and that the selective nickel emission might reflect manufactured materials with specific metallurgical properties. The mainstream astronomical community responded with characteristic skepticism to suggestions of artificial origin. Jason Wright of Penn State University and other researchers pointed out that extraordinary claims require extraordinary evidence, and that the observed anomalies, while unusual, remained within the bounds of what might be expected from natural objects formed in exotic environments around different types of stars. Critics noted that 3I Atlas exhibited classic cometary behavior, developing a coma and tail, responding to solar heating in predictable ways, and following a purely gravitational trajectory without the kind of controlled maneuvers that would definitively indicate technological origin. The chemical anomalies, while puzzling, had potential natural explanations that didn't require invoking alien engineering. Yet even skeptics acknowledged that 3I Atlas represented something genuinely unprecedented in our experience. Its combination of unusual chemistry, compact size, vigorous activity, and directional origin from the same region of sky as the WOW signal created a pattern that stretched coincidence to uncomfortable limits. As observations continued into the autumn of 2025, with the object approaching its critical encounters with Mars and the Sun, the question remained open. Was 3I Atlas simply an unusually exotic natural comet, or might it represent something more extraordinary, a technological artifact from beyond our solar system, somehow connected to that mysterious radio transmission from 4 decades earlier? The answer would depend on whether the accumulating anomalies represented the signature of alien engineering or simply our incomplete understanding of how planetary systems form around stars unlike our own Sunday. Part 8. Sagittarius again. In the cosmic game of Connect, the dots that defines much of astronomical detective work, sometimes patterns emerge that are too intriguing to ignore, even when common sense suggests they might be meaningless coincidences. The directional correlation between the WOW signal and 3I Atlas represents exactly this type of tantalizing alignment, significant enough to capture attention, ambiguous enough to resist definitive interpretation. NASA's trajectory analysis confirmed what preliminary observations had suggested. 3I Atlas was indeed approaching our solar system from the general direction of Sagittarius. More precisely, its radiant, the point on the celestial sphere from which the object appeared to originate, fell within the same broad region of sky where the WOW signal had been detected 4 decades earlier. This wasn't a precise overlap, given the uncertainties in both measurements, but it was close enough to constitute what astronomers cautiously term positional coincidence. The significance of this alignment depends critically on understanding the angular scales involved. Sagittarius, as mapped by traditional constellation boundaries, spans roughly 30 degrees across the sky, an area equivalent to 600 full moons arranged in a grid pattern. Within this vast celestial real estate, the WOW signal's recently refined position occupies a region roughly 8 arc-minutes across, while 3I Atlas's radiant covers a similarly sized uncertainty ellipse displaced by a few degrees. From a statistical perspective, finding 2 unusual objects within the same constellation isn't particularly surprising. Sagittarius covers approximately 1/15 of the entire celestial sphere, so random chance alone would predict that roughly 7% of all anomalous phenomena should appear to originate from this direction. With only 2 data points, statistical analysis becomes essentially meaningless. You can't establish patterns from a sample of 2. Yet the particular choice of constellation adds layers of significance that transcend mere statistics. Sagittarius isn't just any random patch of sky. It's the direction toward our galaxy's most active and populated region. When we look toward these familiar stellar patterns, we're gazing directly into the gravitational and energetic heart of the Milky Way, where star densities reach levels unimaginable in our local cosmic neighborhood. The galactic center environment presents both opportunities and challenges for potential extraterrestrial civilizations. The dense stellar populations could support vast numbers of planetary systems within relatively compact regions, creating conditions ideal for establishing interstellar communication networks or staging areas for deep space exploration. Conversely, the intense radiation fields and frequent gravitational disruptions might make stable planetary systems difficult to maintain, forcing any indigenous life to develop extraordinary technological capabilities simply to survive. From a SETI strategic perspective, the galactic center region represents an obvious target for both transmission and reception of interstellar signals. If advanced civilizations wanted to establish galaxy-wide communication networks, placing broadcast facilities near the galactic center would maximize coverage while minimizing energy requirements. Similarly, any civilization attempting to survey the galaxy for signs of intelligence would naturally focus their attention on the regions most likely to harbor large numbers of technological species. This strategic logic influenced early SETI search strategies and continues to shape modern programs. The galactic center's combination of high stellar density and natural radioactivity makes it both the most promising and most challenging region for signal detection. It's where you'd most expect to find evidence of extraterrestrial intelligence, but also where such evidence would be most difficult to distinguish from exotic natural phenomena. The directional correlation between our two mysteries becomes even more intriguing when considered in the context of galactic dynamics. Objects ejected from planetary systems in the galactic center region would naturally disperse throughout the galaxy over millions of years, potentially reaching our local neighborhood after extraordinarily long journeys through interstellar space. If 3I Atlas did originate from somewhere along the Sagittarius sightline, it might represent a fossil remnant of planetary system formation from the galaxy's most active stellar nursery. But here's where the apparent coincidence becomes truly puzzling: the timing. If 3I Atlas has been wandering through interstellar space for millions or billions of years since its ejection from some distant planetary system, what are the odds it would arrive during the same historical epoch when humans developed radio astronomy and happened to detect an unexplained signal from the same general direction? This temporal coincidence adds a layer of implausibility that stretches random chance explanations to their limits. The universe has existed for 13.8 billion years. Human civilization has possessed radio technology for less than 150 years. The probability that two genuinely unrelated phenomena would converge on our tiny planet during this cosmically brief window seems vanishingly small. Of course, these timing arguments cut both ways. If 3I Atlas were somehow artificially directed toward our solar system, either as an autonomous probe or as part of some vast interstellar communication network, then its arrival during humanity's radio-capable era would make perfect sense. The object would represent a deliberate response to our growing technological visibility, rather than a coincidental encounter with cosmic debris. Such scenarios require extraordinary evidence to be taken seriously, and current observations of 3I Atlas provide nothing approaching the technological signatures that would be necessary to support artificial origin hypotheses. The object behaves like a comet, displays cometary spectral characteristics, and follows a purely gravitational trajectory. Its anomalous chemistry and unusual activity levels, while puzzling, remain within the bounds of what might be expected from natural objects formed in exotic environments. Yet the coincidence persists, nagging at the edges of scientific consciousness like an unsolved equation. Two of the most perplexing anomalies in modern astronomy, separated by nearly half a century, both pointing back toward the same region of sky where our galaxy's most extreme environments create conditions unlike anything in our local cosmic experience. Perhaps the correlation reflects nothing more than observer bias. Humans are pattern-seeking creatures who find connections even in random data. Perhaps it indicates something more profound about the galactic center region as a source of unusual phenomena. Or perhaps, just perhaps, it suggests that our cosmic neighborhood is more active and interconnected than we've dared to imagine. The question of whether these directional correlations represent genuine physical connections or mere coincidence will likely remain open until we accumulate much larger samples of both interstellar visitors and unexplained radio signals. The Legacy Survey of Space and Time, scheduled to begin operations later this decade, should discover hundreds or thousands of additional interstellar objects, revealing whether 3I Atlas represents a typical example or a genuine anomaly. Similarly, advances in radio astronomy sensitivity and data processing capabilities continue expanding our ability to detect and analyze transient signals like the WOW transmission. If similar bursts occur from the Sagittarius direction, particularly if they coincide with 3I Atlas's passage through our solar system, the coincidence explanation would become increasingly difficult to maintain. Until then, we're left with questions rather than answers, patterns rather than explanations. The universe has presented us with two mysteries from the same patch of sky, challenging us to determine whether we're witnessing random cosmic coincidence or the first hints of something far more extraordinary than we ever dared to contemplate. As 3I Atlas continues its journey toward the inner solar system, every observation brings us closer to resolving these questions, or deepening the mystery even further. Part 9. The Timeline of Encounters. The celestial clockwork that governs 3I Atlas's journey through our solar system has been calculated with the precision that only gravitational mechanics can provide. Unlike the mysterious timing of the WOW signal, which appeared once and vanished into history, our interstellar visitor follows a predictable schedule that offers multiple opportunities for detailed observation and, perhaps, for answers to questions that have puzzled us for decades. The first major encounter approaches rapidly. In early October 2025, 3I Atlas will sweep past Mars at a distance of approximately 30 million kilometers, close enough for spacecraft in the Martian system to obtain unprecedented views of an interstellar object. The European Space Agency has confirmed that several of their operational Mars orbiters, including the ExoMars Trace Gas Orbiter and Mars Express, will attempt coordinated observations during this flyby. This Mars encounter represents far more than a mere observational opportunity. For the first time in human history, we'll have spacecraft positioned to study an interstellar visitor from multiple angles simultaneously, providing stereoscopic views that could reveal details about the object's shape, rotation, and surface properties impossible to obtain from Earth-based telescopes alone. The geometry of the encounter will also allow precise measurements of 3I Atlas's gravitational influence on the spacecraft, potentially constraining the object's mass and internal structure. The timing of the Mars flyby, occurring around October 2nd and 3rd, coincides with 3I Atlas's period of maximum activity as solar heating reaches peak intensity. Spectroscopic observations during this window should reveal the full extent of the object's unusual chemistry, particularly whether the mysterious nickel emissions persist, and whether iron finally begins appearing in detectable quantities as internal temperatures rise. Following its Martian encounter, 3I Atlas will continue its inward trajectory toward perihelion, the point of closest approach to the Sunday. This critical milestone, calculated to occur on October 29th and 30th, will bring the object within approximately 1.4 astronomical units of our star, placing it inside the orbit of Mars, but well outside Earth's path. Perihelion represents the moment of maximum stress for any cometary nucleus. Solar radiation reaches peak intensity, driving sublimation rates to their highest levels and potentially triggering dramatic changes in the object's appearance and behavior. If 3I Atlas harbors any unexpected characteristics, unusual internal structures, exotic materials, or technological components, they would most likely reveal themselves during this period of maximum heating. Unfortunately, the timing of perihelion creates significant observational challenges. From Earth's perspective, 3I Atlas will appear dangerously close to the Sun in our sky, making ground-based observations extremely difficult or impossible for several weeks. Only space-based telescopes with appropriate solar shielding will be able to monitor the object during its closest solar approach, placing extraordinary demands on observing time allocation for facilities like Hubble and the James Webb Space Telescope. The object will remain lost in solar glare until early December, when its continued orbital motion finally carries it far enough from the Sun to become visible to ground-based telescopes once again. This reappearance marks the beginning of 3I Atlas's outbound journey, as it begins the long voyage back toward interstellar space, carrying whatever secrets its solar encounter may have revealed. December 19th, 2025, brings 3I Atlas to its closest approach to Earth, approximately 270 million kilometers, roughly twice the distance from our planet to the Sunday. While this may seem disappointingly remote compared to the spectacular close approaches of famous comets like Hale-Bopp or Hyakutake, it represents an optimal balance between observational opportunity and gravitational influence. This Earth encounter offers our best chance to search for any radio emissions that might emanate from 3I Atlas itself. If the object were somehow connected to the WOW signal, if both represented components of some vast interstellar communication effort, then the period around closest approach would provide ideal conditions for signal detection. The geometry would minimize Doppler effects, the relatively short distance would maximize signal strength, and the object's position in our sky would allow continuous monitoring by radio telescopes worldwide. The Earth flyby also coincides with 3I Atlas's transition from inbound to outbound trajectory, a period when any hidden propulsion systems or controlled maneuvers would most likely reveal themselves. Natural objects follow purely gravitational paths that can be predicted with extraordinary precision. Any deviation from these calculated trajectories, even tiny accelerations measured in millimeters per second, could indicate technological origin. As 2026 begins, 3I Atlas will continue its outbound journey toward a final encounter with the outer solar system. On March 16th, the object will pass within approximately 0.36 astronomical units of Jupiter, roughly 54 million kilometers from the giant planet's cloud tops. This represents the closest approach to any major planet during the entire passage, offering unique opportunities for gravitational studies and potentially spacecraft observations. The proposed Jupiter encounter has sparked considerable interest among mission planners. NASA's Juno spacecraft, currently orbiting Jupiter and studying the planet's deep structure, could theoretically be redirected to observe 3I Atlas during its passage. However, such a maneuver would require substantial fuel expenditure and might compromise Juno's primary mission objectives. Similar considerations apply to the European Space Agency's JUICE mission, scheduled to arrive in the Jovian system around the same time. Even without dedicated spacecraft encounters, the Jupiter flyby will provide valuable scientific data. Ground-based telescopes will be able to observe 3I Atlas against the backdrop of Jupiter's complex magnetosphere, potentially revealing how interstellar objects interact with planetary magnetic fields. The encounter will also offer final opportunities to study the object's coma and tail before it begins its irreversible journey back to interstellar space. Beyond March 2026, 3I Atlas will gradually fade from observational reach as it recedes into the outer solar system and eventually back into the cosmic void. Unlike objects gravitationally bound to our Sun, which follow elliptical orbits that eventually bring them back to the inner system, 3I Atlas will never return. This passage represents humanity's one and only opportunity to study this particular messenger from the stars. The entire observational campaign, from discovery in July 2025 through final observations in late 2026, spans roughly 18 months, an unprecedented window for studying an interstellar visitor. This extended timeline allows for coordinated observations across multiple wavelengths, detailed studies of compositional evolution as the object responds to changing solar heating, and systematic searches for any anomalous phenomena that might distinguish 3I Atlas from natural comets. Perhaps most importantly, this timeline provides multiple opportunities to search for radio emissions at the frequencies where the WOW signal appeared 4 decades ago. Each close approach to Mars, the Sun, Earth, and Jupiter represents a potential trigger event, a moment when any hidden transmitters might activate or when changing geometry might allow us to detect signals that were previously obscured. The cosmic choreography is perfectly arranged. All we need to do is watch, listen, and remain open to the possibility that this interstellar visitor might carry more than just exotic chemistry and unusual physics. It might carry answers to questions we've been asking since that remarkable night in 1977 when Jerry Eman first scrawled "Wow" across a computer printout and launched nearly half a century of speculation about what might be waiting for us among the stars. Part 10. Scientists divided. In the normally collegial world of astronomical research, where scientific disagreements typically unfold through carefully worded journal papers and polite conference presentations, 3I Atlas has triggered something approaching intellectual combat. The object's unusual characteristics have crystallized fundamental philosophical divisions about how we interpret anomalous data and what standards of evidence we require before entertaining extraordinary explanations. The mainstream consensus, represented by institutions like NASA, the European Space Agency, and major observatories worldwide, maintains that 3I Atlas represents a natural comet, admittedly an unusual one, but well within the bounds of what might be expected from objects formed around different types of stars. This conservative interpretation emphasizes the object's fundamentally comet-like behavior. It develops a coma and tail, responds predictably to solar heating, and follows a purely gravitational trajectory through our solar system. According to this view, the chemical anomalies that have sparked so much speculation, the carbon dioxide dominance, the nickel without iron emission, the apparent overperformance relative to size, reflect our incomplete understanding of how comets form in exotic stellar environments rather than evidence of artificial origin. Dr. Alan Fitzsimmons of Queen's University Belfast, a leading expert on small solar system bodies, argues that discovering weird chemistry in interstellar objects should be expected rather than surprising. We've only studied 3 confirmed interstellar visitors, Fitzsimmons notes in recent interviews. Drawing conclusions about what's normal or abnormal from such a tiny sample is like trying to understand human diversity by meeting 3 random strangers. 3I Atlas might seem unusual compared to solar system comets, but it's probably typical of objects formed around stars with different compositions, temperatures, or evolutionary histories. This mainstream perspective receives strong support from updated Hubble Space Telescope observations that have refined estimates of 3I Atlas's size and structure. The latest measurements suggest a nucleus no larger than 5.6 kilometers across, with some analyses favoring dimensions closer to 300 meters. These constraints help explain the object's apparently vigorous activity. Smaller bodies have higher surface area to volume ratios, allowing more efficient volatile release when heated by solar radiation. But not everyone finds these conventional explanations satisfying. Avi Loeb, the controversial Harvard astrophysicist who previously argued that Oumuamua might represent alien technology, has turned his attention to 3I Atlas with characteristic boldness. In a series of blog posts, interviews, and preliminary research papers, Loeb contends that the accumulating anomalies suggest possible artificial origin. Natural selection doesn't care about our comfort level, Loeb argues. It only cares about evidence. When we see an object displaying multiple characteristics that deviate from our expectations, unusual chemistry, unexpected activity levels, precise orbital parameters, we should consider all possible explanations, including technological ones. Loeb's analysis focuses particularly on what he terms the coincidence problem, the temporal alignment between 3I Atlas's arrival and the WOW signals' 48th anniversary, combined with their shared directional origin from Sagittarius, creates what he describes as a probability deficit that demands explanation. He suggests that both phenomena might represent components of an interstellar probe mission designed to assess humanity's technological development. The scientific community's response to Loeb's speculations has been characteristically blunt. Jason Wright of Penn State University, a respected SETI researcher who has spent years developing rigorous methods for identifying potential technosignatures, argues that extraordinary claims require extraordinary evidence, and that 3I Atlas fails to meet this standard. AV is looking at statistical anomalies and inferring causation where only correlation exists. Wright explains, yes, 3I Atlas has unusual properties. But unusual doesn't mean impossible, and possible natural explanations still exist for every observed characteristic. Until we see definitively artificial signatures, controlled maneuvers, structured radio emissions, or materials that can't be produced by natural processes, we should stick with conventional explanations. Wright points to several recent developments that support natural interpretations of 3I Atlas's behavior. Detailed thermal modeling suggests the object's carbon dioxide dominance could result from formation in the outer regions of planetary systems around stars hotter than our Sunday. The nickel emissions without corresponding iron detection might reflect unusual mineral compositions or thermal processing that preferentially releases one element before the other. Even the apparent overperformance could be explained by internal structures, perhaps porous or fractured nuclei, that maximize volatile exposure to solar radiation. The size debate has become particularly contentious, with different research teams reaching conflicting conclusions about 3I Atlas's physical dimensions. Early reports suggested the object might be substantially larger than current Hubble constraints allow, leading to speculation about unusual density or internal structure. But improved observations have consistently favored smaller sizes, bringing the object's properties closer to conventional comet expectations. Dr. Maria Womack of the University of South Florida, who leads several ongoing 3I Atlas observation campaigns, emphasizes that resolving these disputes requires more data rather than more speculation. We're seeing journalists and bloggers making definitive statements about what this object is or isn't based on preliminary observations, she notes. Science doesn't work that way. We need months or years of careful analysis before we can draw reliable conclusions. The controversy extends beyond pure scientific questions to encompass broader issues about how astronomy should respond to anomalous discoveries. Some researchers worry that premature speculation about alien technology damages astronomy's reputation and makes it more difficult to secure funding for legitimate SETI research. Others argue that dismissing unconventional possibilities too quickly might cause us to overlook genuine discoveries. This tension reflects deeper philosophical divisions within the scientific community about the nature of evidence and the role of speculation in research. Conservative researchers emphasize the importance of exhausting natural explanations before considering exotic alternatives. They point to astronomy's history of discovering new natural phenomena that initially appeared impossible or artificial. Pulsars, gamma-ray bursts, and fast radio bursts all triggered similar speculation before revealing their true nature. Progressive researchers counter that scientific breakthroughs often require willingness to consider paradigm-shifting possibilities. They note that SETI research itself began with scientists willing to take seriously the possibility that radio signals might originate from extraterrestrial civilizations. Without such intellectual courage, they argue, we risk missing discoveries that could transform our understanding of our place in the universe. The debate has been complicated by media coverage that often fails to distinguish between peer-reviewed research and preliminary speculation. Headlines declaring 3I Atlas to be an alien probe, or definitively natural, appear regularly, despite the fact that scientific consensus remains elusive. This coverage influences public perception and potentially affects funding decisions for future research. Professional organizations have begun developing guidelines for communicating about potentially anomalous discoveries. The International Astronomical Union has emphasized the importance of presenting multiple hypotheses rather than favoring sensational explanations. SETI organizations stress the need for rigorous verification procedures before announcing any claims of extraterrestrial origin. Meanwhile, observational campaigns continue generating new data that both support and challenge various interpretations of 3I Atlas. Recent spectroscopic observations have confirmed the persistence of unusual chemical signatures while revealing additional complexities in the object's composition. Photometric studies have documented changes in brightness and color that might indicate surface heterogeneity or rotational variations. Perhaps most significantly, several research teams have begun coordinated efforts to search for radio emissions from 3I Atlas itself. Using facilities ranging from the Very Large Array to the Green Bank Telescope, astronomers are systematically monitoring frequencies around the hydrogen line and other potentially significant wavelengths. These searches represent the first systematic attempt to detect artificial signals from an interstellar visitor. The radio silence observed so far provides ammunition for both sides of the artificial origin debate. Skeptics argue that the lack of detectable transmissions supports natural explanations. Genuine alien probes would presumably communicate with their creators or announce their presence to local civilizations. Advocates counter that sophisticated probes might remain silent except during specific trigger events or might use communication methods we haven't yet learned to detect. As 3I Atlas approaches its critical encounters with Mars and the Sun, the stakes of this scientific controversy continue rising. If the object begins displaying definitively artificial characteristics, controlled maneuvers, structured radio emissions, or impossible material properties, then current debates will seem quaint in retrospect. If it continues behaving like an exotic but natural comet, then the episode will serve as a valuable lesson about the dangers of premature speculation. Either way, 3I Atlas has already succeeded in forcing the scientific community to confront fundamental questions about how we evaluate evidence, interpret anomalies, and remain open to discoveries that might challenge our most basic assumptions about the universe we inhabit. The next few months will determine whether these debates represent growing pains in humanity's expanding cosmic awareness or simply another chapter in the long history of mistaking the unusual for the impossible. Part 11. Coincidence or contact? The human brain evolved to find patterns in chaos, to extract meaning from randomness, and to construct narratives that transform disconnected events into coherent stories. This remarkable cognitive ability allowed our ancestors to survive in environments where distinguishing between meaningful signals and background noise could mean the difference between life and death. But in our modern quest to understand cosmic mysteries, this same pattern-seeking instinct can lead us astray, creating connections where none exist and finding significance in mere coincidence. The apparent relationship between the WOW signal and 3I Atlas represents a perfect case study in the psychology of pattern recognition. Two anomalous phenomena, separated by nearly half a century, both originating from the same general region of sky. The coincidence feels too meaningful to ignore, too precisely orchestrated to be random chance. Our minds rebel against accepting such alignment as mere statistical accident. Yet when we examine the evidence dispassionately, the connections begin to seem less compelling. The WOW signal's refined position, while more precise than originally known, still encompasses a region of sky roughly 8 arcminutes across. 3I Atlas's radiant covers a similarly sized uncertainty ellipse displaced by several degrees. In cosmic terms, this represents a missed distance of millions of light-years, hardly the precision we might expect from a coordinated communication effort. The temporal correlation presents similar ambiguities. If 3I Atlas has been wandering through interstellar space for millions or billions of years since its ejection from some distant planetary system, its arrival during humanity's radio-capable era could represent either extraordinary coincidence or evidence of deliberate targeting. Without knowing the object's true age and origin, we cannot distinguish between these possibilities. The directional correlation towards Sagittarius adds layers of complexity rather than clarity. This constellation encompasses some of the most radioactive regions of our galaxy, where natural emissions from countless astrophysical sources create a cacophony of signals that would challenge any attempt to detect artificial transmissions. Finding anomalous phenomena from this direction might reflect the region's inherent activity rather than evidence of technological civilizations. Statistical analysis offers little guidance when dealing with such small sample sizes. With only one confirmed unexplained radio signal and 3 interstellar visitors in human history, we cannot establish baseline rates for either phenomenon. Are such events common or rare? Do they typically cluster in space and time or appear randomly? Our cosmic census remains too incomplete to support meaningful statistical conclusions. The Maser hypothesis for the WOW signal, which has gained considerable support among astronomers in recent years, further complicates any connection to 3I Atlas. If the original transmission represented a natural hydrogen maser triggered by some distant energetic event, then its relationship to our current interstellar visitor becomes purely coincidental. Two unrelated natural phenomena from the same region of sky, linked only by human imagination and the tendency to find meaning in randomness. Yet dismissing the correlation entirely requires its own leap of faith. The universe contains approximately 2 trillion galaxies, each hosting hundreds of billions of stars, creating countless opportunities for the emergence of technological civilizations. If even a tiny fraction of these worlds develop spacefaring capabilities and interstellar communication networks, then the galaxy might be far more active and interconnected than our current observations suggest. From this perspective, the correlation between the WOW signal and 3i Atlas could represent our first glimpse of this hidden cosmic infrastructure. The original transmission might have served as an announcement or beacon, while the interstellar visitor represents a physical probe dispatched to investigate worlds that demonstrated radio listening capabilities. Such a scenario would explain both the timing of 3i Atlas's arrival during humanity's technological adolescence and its approach from the same region that produced the original signal. Testing this hypothesis requires identifying characteristics that would distinguish between coincidence and genuine connection. The most obvious would be radio emissions from 3i Atlas itself, particularly if they occurred at frequencies related to the original WOW signal. Structured transmissions, modulated signals, or bursts timed to coincide with the object's closest approaches to major planets would provide strong evidence of artificial origin. Alternatively, the absence of such signals might support the coincidence interpretation. If 3i Atlas were a genuine alien probe responding to the WOW signal, we might reasonably expect it to attempt communication with Earth or at least transmit data to its creators. The radio silence observed so far suggests either sophisticated stealth capabilities or natural origin. Physical characteristics offer additional testing opportunities. Genuine technological artifacts should display material properties, structural features, or behavioral patterns that distinguish them from natural objects. Controlled maneuvers, impossible thermal signatures, or surface compositions that couldn't result from natural processes would provide definitive evidence of artificial origin. The burden of proof remains extraordinarily high for any claims of extraterrestrial technology. The history of astronomy is littered with phenomena that initially appeared artificial but later revealed natural explanations. Pulsars were briefly considered potential alien beacons until their true nature as rotating neutron stars became clear. Fast radio bursts triggered similar speculation before we understood their cosmic origins. This historical context doesn't invalidate the possibility that 3i Atlas represents genuine alien technology. It simply emphasizes the need for extraordinary evidence to support extraordinary claims. The object's unusual characteristics, while intriguing, remain within the bounds of what might be expected from natural comets formed in exotic stellar environments. Perhaps the most honest assessment acknowledges both the appeal and the limitations of the connection hypothesis. The correlation between the WOW signal and 3i Atlas provides a compelling narrative framework that helps organize our thinking about these mysteries. It generates testable predictions about what we might observe during the object's passage through our solar system. It motivates coordinated observation campaigns that will yield valuable scientific data regardless of their ultimate conclusions. But we must remain vigilant against confirmation bias, the tendency to interpret ambiguous evidence as supporting our preferred explanations. Every anomalous characteristic of 3i Atlas, every unusual signal detected during radio searches, every unexpected behavior will be scrutinized for potential connections to the WOW transmission. This scrutiny is scientifically valuable, but it must be balanced against equally rigorous consideration of conventional explanations. The coming months will provide crucial tests of the connection hypothesis. As 3i Atlas approaches Mars, rounds the Sun, and passes closest to Earth, we will have unprecedented opportunities to search for artificial signals, document anomalous behaviors, and analyze the object's physical and chemical properties with extraordinary precision. If these observations reveal definitive evidence of technological origin, then the correlation with the WOW signal will transform from intriguing coincidence to profound discovery. If they support conventional comet interpretations, then we will have learned valuable lessons about both the nature of interstellar objects and the psychology of pattern recognition in scientific research. Either way, the exercise of taking the correlation seriously, of designing tests and conducting observations based on the possibility that these phenomena might be connected, represents the scientific method at its best. We form hypotheses based on available evidence, design experiments to test those hypotheses, and remain prepared to revise our conclusions based on new data. In a universe where we have detected only one unexplained radio signal and observed only 3 interstellar visitors, every correlation deserves careful consideration. The alternative, dismissing patterns before we fully understand them, risks overlooking discoveries that might transform our understanding of our cosmic neighborhood and our place within it. Part 12. The Message in Motion Hypothesis. In the realm of speculative science, few ideas capture the imagination quite like the possibility that we might be witnessing a coordinated interstellar communication effort, a cosmic conversation conducted across decades and light years, with messages encoded not just in radio waves but in the physical movement of objects through space itself. The message in motion hypothesis represents perhaps the most audacious attempt to connect the WOW signal with 3-eye atlas, proposing that both phenomena represent components of a sophisticated alien communication protocol. According to this speculative framework, the WOW signal served as an initial announcement, a brief radio transmission designed to capture the attention of any technologically capable civilizations within range. The signal's appearance at the hydrogen line frequency would ensure recognition by any species that had developed radio astronomy, while its intense, narrow-band characteristics would distinguish it clearly from natural background emissions. But here's where the hypothesis becomes truly extraordinary. Rather than sending additional radio transmissions that might be missed or misinterpreted, the hypothetical alien civilization dispatched a physical probe to serve as a follow-up message. 3-eye atlas, in this scenario, represents a sophisticated technological artifact disguised as a natural comet, carrying information, instruments, or even representatives from its creators on a multi-decade journey to our solar system. The apparent 48-year delay between signal and visitor would make perfect sense in this context. Radio waves travel at the speed of light, covering the distance from nearby star systems in years or decades. Physical objects, even those equipped with advanced propulsion systems, would require much longer transit times. The timing suggests an origin perhaps 10 to 30 light-years from Earth, close enough for radio communication, far enough to require substantial time for physical travel. This hypothesis would elegantly explain several puzzling aspects of both phenomena. The WOW signal's failure to repeat becomes understandable if it was designed as a one-time announcement rather than an ongoing beacon. The signal's precise frequency and timing would reflect careful planning by beings who understood human radio astronomy capabilities and monitoring schedules. 3-eye atlas's unusual characteristics, its carbon dioxide-rich chemistry, selective metal emissions, and apparent overperformance relative to size, might represent sophisticated camouflage designed to mask technological components within an apparently natural shell. The object's retrograde, low-inclination orbit could indicate controlled trajectory adjustments rather than random interstellar dynamics. But how would we test such an extraordinary claim? The hypothesis generates several specific, falsifiable predictions about what we should observe as 3-eye atlas continues its passage through our solar system. First, we might detect structured radio emissions from the object itself, particularly during its closest approaches to major planets. These transmissions might occur at frequencies related to the original WOW signal, perhaps harmonics of the hydrogen line or other mathematically significant wavelengths. The signals might display modulation patterns, frequency drifts, or timing sequences that would be impossible to produce through natural processes. Second, the object might display non-gravitational accelerations inconsistent with normal cometary outgassing. While Oumuamua exhibited similar anomalous acceleration, it could be explained, though not definitively, by asymmetric volatile release. A genuine technological probe might display controlled maneuvers, trajectory corrections, or propulsion signatures that couldn't be attributed to natural sublimation processes. Third, detailed spectroscopic analysis might reveal material compositions impossible to achieve through natural processes. Industrial metals in specific ratios, artificially synthesized compounds, or isotopic signatures inconsistent with stellar nucleosynthesis could indicate technological origin. The mysterious nickel without iron emission already observed might represent just the beginning of unusual chemical revelations. Fourth, thermal observations might detect heat signatures inconsistent with pure solar heating. Internal power sources, electrical systems, or mechanical components could produce infrared emissions with spectral characteristics or temporal variations that would betray artificial origin. However, each of these potential tests faces significant challenges and alternative explanations. Radio emissions from comets, while rare, have been detected before, typically caused by interactions between the solar wind and the cometary coma. Distinguishing between natural plasma phenomena and artificial transmissions requires careful analysis of signal characteristics, frequency stability, and polarization properties. Non-gravitational accelerations present similar interpretive challenges. The Oumuamua controversy demonstrated how difficult it can be to distinguish between exotic outgassing scenarios and hypothetical propulsion systems. 3I Atlas's active cometary behavior might actually complicate such analyses by providing obvious natural mechanisms for trajectory changes. Material composition anomalies could result from formation in exotic stellar environments rather than artificial manufacturing. Stars with different masses, metallicities, and evolutionary histories might produce planetary systems with radically different chemical abundances. What appears unusual by solar system standards might be perfectly normal elsewhere in the galaxy. Thermal anomalies face similar interpretive difficulties. Cometary nuclei can display complex thermal behavior due to internal structure variations, subsurface volatile pockets, or seasonal effects related to rotational orientation. Distinguishing between these natural phenomena and potential artificial heat sources requires extremely precise measurements and sophisticated modeling. The message in motion hypothesis also confronts broader logical challenges. If an advanced civilization wanted to communicate with humanity, why choose such an elaborate and time-consuming method? Radio transmissions offer nearly instantaneous communication across interstellar distances, while physical probes require decades or centuries for delivery. The resource investment would be enormous, and the risk of mission failure substantial. Moreover, disguising a technological probe as a natural comet seems unnecessarily complex and potentially counterproductive. If the goal were communication or contact, why not design the probe to be obviously artificial? Clear technological signatures would eliminate ambiguity and ensure rapid recognition by the target civilization. These logical objections don't definitively invalidate the hypothesis, but they do highlight the extraordinary nature of the claims involved. Perhaps alien communication strategies operate according to principles we don't yet understand. Maybe the physical probe carries information or capabilities that couldn't be transmitted via radio waves. Possibly the camouflage reflects caution about revealing technological capabilities to potentially hostile civilizations. The hypothesis also raises profound questions about the nature and motivations of hypothetical alien civilizations. What kind of beings would conduct communication across such vast scales of space and time? How would they coordinate complex multi-decade mission profiles? What information or objectives would justify such elaborate efforts? These questions venture into pure speculation, but they illustrate how seriously considering the message in motion hypothesis forces us to contemplate possibilities that stretch our understanding of intelligence, technology, and cosmic communication strategies. As 3I Atlas approaches its critical encounters with Mars and the Sun, the hypothesis faces its most rigorous tests. If the object begins displaying definitively artificial characteristics, controlled maneuvers, structured emissions, or impossible material properties, then the message in motion scenario would transform from wild speculation to revolutionary discovery. If observations continue supporting natural comet interpretations, then the hypothesis will join the long list of imaginative but incorrect explanations for cosmic mysteries. Either outcome will advance our understanding, either by revealing the first confirmed alien technology, or by teaching us valuable lessons about distinguishing between genuine anomalies and the products of human pattern-seeking psychology. The beauty of science lies not in avoiding bold hypotheses, but in testing them rigorously and honestly. The message in motion hypothesis may be wrong, but taking it seriously enough to conduct careful observations and analyses represents the scientific method at its most adventurous and most valuable. Part 13. The Act of Listening. In the grand symphony of cosmic radio emissions that surrounds our planet every moment of every day, the act of listening for artificial signals requires both technological sophistication and profound patience. As 3I Atlas continues its journey through our solar system, radio astronomers around the world are preparing for what may be the most intensive SETI listening campaign in history, a coordinated effort to detect any transmissions that might emanate from our mysterious interstellar visitor. The listening strategy focuses on the most promising observational windows, times when geometry, proximity, and gravitational dynamics create optimal conditions for signal detection. The Mars flyby in early October represents the first critical opportunity, as 3I Atlas passes within 30 million kilometers of the red planet. If the object were programmed to respond to planetary encounters, perhaps triggered by gravitational fields or magnetic environments, this would be the moment for initial activation. The perihelion passage in late October offers even more dramatic possibilities. As 3I Atlas rounds the Sun at its closest approach, solar heating reaches maximum intensity, potentially triggering changes in the object's behavior or revealing hidden capabilities. The intense radiation environment might activate dormant systems, power up communication arrays, or trigger programmed responses designed to announce the probe's presence to any observing civilizations. But perhaps the most significant window occurs during 3I Atlas's closest approach to Earth in mid-December. At a distance of approximately 270 million kilometers, any signals originating from the object would reach maximum strength while minimizing Doppler effects that could complicate frequency analysis. The geometry would allow continuous monitoring by radio telescopes worldwide as Earth's rotation sweeps different facilities into optimal viewing positions. The search frequencies focus primarily on the waterhole region between 1420 and 1670 MHz, with special attention to the exact frequency where the WOW signal appeared 4 decades ago. But modern SETI protocols recognize that alien communication systems might operate according to principles we don't yet understand, so the searches will span much broader spectral ranges, from low-frequency radio waves up through microwave and millimeter wavelengths. The Breakthrough Listen project, funded by Russian billionaire Yuri Milner, has already begun dedicating substantial observing time to 3I Atlas monitoring. Their global network of radio telescopes includes the Green Bank Telescope in West Virginia, the Parkes Observatory in Australia, and the Meerkat Array in South Africa. These facilities offer complementary capabilities, different frequency ranges, observing geometries, and sensitivity levels that together provide comprehensive coverage of potential signal characteristics. China's 500-meter aperture spherical telescope, the world's largest single-dish radio telescope, has also joined the campaign. FAST's enormous collecting area makes it particularly sensitive to weak signals, while its location provides coverage of sky regions inaccessible to Northern Hemisphere facilities. The telescope's recent commissioning for SETI observations adds unprecedented sensitivity to the search effort. The technical challenges of detecting artificial signals from 3I Atlas extend far beyond simple sensitivity requirements. Any genuine extraterrestrial transmission would likely display characteristics that distinguish it from natural radio sources, perhaps complex modulation patterns, precise frequency stability, or structured information content. Modern signal processing algorithms can identify these signatures even when embedded in noise, but they require careful calibration to avoid false positives. Doppler analysis presents particular opportunities and challenges. 3I Atlas's motion through our solar system creates predictable frequency shifts for any signals originating from the object. Natural sources would display Doppler patterns that precisely match the object's trajectory, while artificial transmissions might show additional frequency drifts designed to compensate for relative motion or encode information in the changing signal characteristics. Polarization measurements add another dimension to the search strategy. Radio waves carry information in their electric field orientations, and artificial transmissions might display polarization signatures that would be difficult or impossible to produce through natural processes. Circular polarization, rapid polarization changes, or structured polarization patterns could indicate technological origin. The listening campaign also includes searches for optical and infrared signals that might accompany radio transmissions. Pulsed laser communications, thermal signatures from artificial heating, or modulated reflections of sunlight could provide complementary evidence of technological activity. These multi-wavelength approaches increase the probability of detection while providing redundant confirmation of any positive signals. Citizen science plays an increasingly important role in modern SETI searches. Projects like SETI at home have demonstrated the power of distributed computing for analyzing vast amounts of radio data, while amateur astronomers with sophisticated equipment can contribute valuable observations. The 3I Atlas campaign provides opportunities for both professional and amateur participation in what may be humanity's most significant search for extraterrestrial intelligence. Time domain analysis represents another crucial component of the listening strategy. Rather than searching only for continuous signals, the campaign monitors 3I Atlas for brief bursts, periodic transmissions, or signals that appear only during specific geometric configurations. Such intermittent signals might be easier to distinguish from natural background sources while requiring less power from potential alien transmitters. The psychological and sociological aspects of the listening campaign deserve equal consideration alongside the technical challenges. If artificial signals are detected, the discovery would trigger carefully planned verification and notification protocols developed by the international SETI community. Independent confirmation by multiple telescopes would be required before any public announcements, followed by detailed analysis to rule out terrestrial interference or natural explanations. But negative results would be equally significant, though perhaps less dramatic. The absence of detectable signals would place valuable constraints on the power and sophistication of any hypothetical alien technology, while demonstrating humanity's growing capabilities for interstellar communication monitoring. Each null result narrows the parameter space for potential extraterrestrial civilizations and refines our understanding of cosmic communication challenges. The 3I Atlas listening campaign also serves as a technological proving ground for future SETI efforts. The techniques, algorithms, and coordination protocols developed during this intensive monitoring period will establish standards for investigating other anomalous objects or signals. The campaign represents a dress rehearsal for humanity's response to potential extraterrestrial contact. Educational and inspirational aspects of the listening effort extend its impact far beyond the scientific community. Students around the world are participating in data analysis projects, while public outreach programs explain the search techniques and their significance. The campaign demonstrates science in action, showing how researchers respond to extraordinary possibilities with rigorous methodology and international cooperation. As radio telescopes around the world point toward 3I Atlas during its passage through our solar system, they carry with them the accumulated hopes and curiosity of our entire species. The act of listening represents humanity at its most optimistic and adventurous, willing to invest substantial resources and effort based on the slim possibility that we might not be alone. Whether the cosmic silence continues or gives way to the first confirmed artificial signal from another world, the listening campaign will mark a watershed moment in our relationship with the universe. We are no longer passive observers of cosmic phenomena, but active participants in a search that could transform our understanding of life, intelligence, and our place in the cosmic community. The universe is vast and largely silent, but we are listening with unprecedented sensitivity and sophistication. If anyone out there is trying to communicate, we are finally ready to hear their message. Part 14. The Bigger Picture. Beyond the immediate mysteries surrounding 3I Atlas and its potential connection to the WOW signal lies a broader transformation in our understanding of the cosmic environment we inhabit. This interstellar visitor represents far more than a single anomalous object. It embodies our species' growing recognition that the universe is dynamic, interconnected, and full of wanderers carrying stories from worlds we may never directly observe. The scientific value of studying interstellar objects extends far beyond SETI considerations into fundamental questions about planetary system, formation, and evolution. Every comet, asteroid, or mysterious wanderer ejected from another star system carries within its chemistry and structure the fossil record of processes that occurred billions of years ago around alien suns. These objects serve as time capsules, preserving information about stellar environments, protoplanetary disk compositions, and the mechanisms by which worlds are born. 3I Atlas's unusual carbon dioxide to water ratio provides a perfect example of this archaeological potential. In our solar system, the abundance patterns of volatile compounds reflect specific conditions that existed during the Sun's formation 4.6 billion years ago. The gas and dust disks surrounding our young star had particular temperature gradients, pressure distributions, and chemical compositions that determined where different materials could condense into solid form. Finding an interstellar comet with dramatically different volatile ratios suggests formation around a star with different properties, perhaps more massive, hotter, or enriched with different abundances of heavy elements. By analyzing these chemical signatures in detail, astronomers can begin reconstructing the conditions that existed in alien planetary systems during their earliest stages of development. The mysterious nickel emissions without corresponding iron detection add another piece to this cosmic puzzle. These elements typically occur together in stellar nucleosynthesis and planetary formation processes, so their apparent separation in 3I Atlas implies unusual chemical or physical processes that don't commonly occur in our local cosmic neighborhood. Understanding the mechanisms responsible for this selective emission could reveal new insights into cometary physics or exotic formation environments. Modern observatory capabilities are perfectly positioned to extract maximum scientific value from 3I Atlas's passage. The James Webb Space Telescope's unprecedented infrared sensitivity allows detailed analysis of molecular emissions that were impossible to detect with previous generations of instruments. Hubble's high-resolution imaging provides constraints on the object's size, shape, and rotation that inform models of its internal structure and composition. Ground-based facilities contribute complementary capabilities through their ability to track 3I Atlas continuously as it evolves during its solar encounter. The Gemini Observatory's documentation of coma and tail development provides real-time monitoring of how the object responds to changing solar heating, while spectroscopic surveys track the appearance and evolution of different molecular species as internal temperatures rise. This coordinated observational campaign represents a new paradigm in astronomical research, the intensive, multi-wavelength study of rare, time-limited phenomena. Unlike stars or galaxies that remain essentially unchanged over human timescales, interstellar visitors offer only brief windows for detailed investigation before disappearing forever into the cosmic void. The lessons learned from 3I Atlas will prove invaluable for studying future interstellar visitors, which are likely to arrive with increasing frequency as our detection capabilities improve. The Legacy Survey of Space and Time, scheduled to begin operations later this decade, will dramatically expand our ability to discover small, fast-moving objects approaching from interstellar space. Current estimates suggest we might detect dozens or hundreds of additional visitors over the next decade. This growing population will transform interstellar objects from individual curiosities into a statistical sample that can reveal broader patterns about planetary system formation throughout the galaxy. We'll begin to understand which types of objects are commonly ejected during planetary system evolution, what chemical signatures characterize formation around different stellar types, and how frequently genuine anomalies occur among the population of interstellar wanderers. The citizen science aspects of 3I Atlas research demonstrate how modern astronomy increasingly relies on distributed networks of observers and data analysts. Amateur astronomers with sophisticated equipment can contribute valuable observations, particularly for monitoring brightness variations, tracking positional changes, and documenting morphological evolution of the coma and tail. Projects like the Unistellar Citizen Science Campaign have already begun collecting data on 3I Atlas from dozens of locations worldwide, providing temporal coverage that would be impossible for individual professional observatories to achieve. This distributed approach not only increases the total amount of data collected, but also helps verify observations and identify potential systematic errors. The broader implications of studying interstellar visitors extend into astrobiology and the search for life beyond Earth. While 3I Atlas shows no obvious signs of hosting biological activity, future visitors might carry organic compounds, complex molecules, or even preserved microorganisms from their original planetary systems. Such discoveries would provide direct evidence about the chemical evolution of life in different cosmic environments. The potential for panspermia, the transfer of life between planetary systems via natural processes, adds another dimension to interstellar object research. If microorganisms can survive the extreme conditions of interstellar space for millions of years, then objects like 3I Atlas might serve as vectors for biological exchange across vast cosmic distances. Detecting such preserved life would revolutionize our understanding of biology's cosmic distribution. Even without biological payloads, interstellar visitors provide crucial data about the galaxy's chemical evolution over cosmic time. Objects ejected billions of years ago preserve information about stellar nucleosynthesis products, supernova enrichment patterns, and heavy element distributions that characterized earlier epochs of galactic history. They serve as archived samples from environments that may no longer exist. The technological and methodological advances driven by interstellar object research benefit astronomy more broadly. Improved algorithms for detecting fast-moving objects enhance our ability to track potentially hazardous asteroids. Better spectroscopic analysis techniques advance our understanding of solar system comets and asteroids. Enhanced international coordination protocols strengthen the global astronomical community's ability to respond rapidly to time-critical discoveries. Perhaps most importantly, studying objects like 3I Atlas forces us to confront the limitations of our current knowledge while remaining open to possibilities that stretch our understanding. The object's anomalous characteristics remind us that the universe continues to surprise us, challenge our assumptions, and reveal phenomena we haven't yet learned to expect. As 3I Atlas continues its journey toward the inner solar system and its critical encounters with Mars, the Sun, and Earth, it carries with it the accumulated curiosity and technological capabilities of our entire species. Every spectrum we collect, every image we capture, and every measurement we make contributes to humanity's expanding understanding of the cosmic environment we share with countless other worlds. Whether 3I Atlas ultimately proves to be an exotic natural comet or something more extraordinary, its passage through our solar system marks a milestone in our species' cosmic maturity. We are no longer isolated observers of distant phenomena, but active participants in a universe that regularly delivers visitors from other worlds, each carrying their own stories and secrets from the vast darkness between the stars. The bigger picture reveals a cosmos far more dynamic and interconnected than previous generations could have imagined, a place where matter, and perhaps even life, routinely travels between star systems, where every world potentially influences every other world, and where the next discovery might fundamentally transform our understanding of our place in the cosmic community. Part 15. Closing Reflection. waiting for the next wow. As we reach the end of our journey through the mysteries surrounding 3I Atlas and its potential connection to the WOW signal, we find ourselves standing at a remarkable juncture in human history. Never before have we possessed such sophisticated tools for investigating cosmic anomalies. Never before have we been so well positioned to detect signs of extraterrestrial intelligence. And never before have we faced such tantalizing possibilities for discovering that we are not alone in the universe. The story we've traced, from that fateful night in 1977 when Jerry Eman first scrawled "Wow" across a computer printout, through decades of follow-up searches and theoretical speculation, to the arrival of our mysterious interstellar visitor in 2025, represents more than just a chronicle of unexplained phenomena. It embodies humanity's persistent refusal to accept easy answers, our willingness to pursue questions even when they lead into uncomfortable uncertainties, and our growing confidence in our ability to investigate the cosmos with scientific rigor. Whether the correlation between the WOW signal and 3I Atlas ultimately proves meaningful or coincidental, both phenomena have already succeeded in advancing our understanding of the universe we inhabit. The original radio transmission demonstrated that our instruments were capable of detecting powerful signals from interstellar distances, validating search strategies and inspiring generations of SETI researchers. It established benchmarks for evidence evaluation that continue to guide our response to anomalous discoveries. 3I Atlas, regardless of its ultimate nature, has provided unprecedented opportunities to study authentic interstellar material with modern analytical techniques. Every spectrum collected, every image captured, and every measurement recorded contributes to our understanding of planetary system formation beyond our local cosmic neighborhood. The object has forced us to expand our models of cometary behavior, confront our assumptions about what constitutes normal chemistry, and develop new methodologies for investigating time-limited phenomena. Perhaps most importantly, both mysteries have demonstrated the power of maintaining epistemic humility, the recognition that our current understanding represents only a small fraction of cosmic reality. The universe continues to surprise us with phenomena that challenge our theories, stretch our imaginations, and remind us that the unknown vastly exceeds the known. The scientific process that has guided our investigation of these mysteries exemplifies humanity's most noble intellectual traditions. We observe carefully, measure precisely, propose hypotheses, test predictions, and remain prepared to revise our conclusions based on new evidence. We distinguish between speculation and fact, label our assumptions clearly, and acknowledge the limitations of our current knowledge. This methodological rigor becomes particularly crucial when investigating phenomena that might represent contact with extraterrestrial intelligence. The potential implications are so profound that extraordinary care must be taken to avoid both premature conclusions and premature dismissals. We must remain open to possibilities that might transform our understanding of our place in the universe while maintaining the skeptical scrutiny that prevents wishful thinking from masquerading as scientific discovery. As 3I Atlas approaches its critical encounters with Mars, the Sun, and Earth over the coming months, radio telescopes around the world will be listening with unprecedented sensitivity for any signals that might emanate from our interstellar visitor. These searches represent more than attempts to validate specific hypotheses. They embody humanity's commitment to remaining alert for messages from beyond our world. The listening campaigns planned for 3I Atlas's passage also serve as preparations for future opportunities. The techniques, protocols, and international coordination mechanisms being developed during this investigation will establish standards for responding to other anomalous objects or signals. We are building the infrastructure for cosmic communication, creating systems capable of detecting, verifying, and responding to potential messages from extraterrestrial civilizations. The educational and inspirational aspects of this investigation extend far beyond the scientific community. Students around the world are participating in data analysis projects. Citizen scientists are contributing observations. and the general public is engaging with questions about our cosmic significance in ways that transcend traditional boundaries between science and philosophy. The search for extraterrestrial intelligence has become a genuinely global, species-wide endeavor. Looking forward, the coming decades promise to bring revolutionary advances in our ability to investigate cosmic mysteries. The legacy survey of space and time will discover hundreds or thousands of additional interstellar visitors, transforming our current sample of 3 objects into a statistical population that can reveal broader patterns about planetary system formation throughout the galaxy. Next-generation radio telescopes will achieve sensitivities that dwarf current capabilities, allowing us to detect much weaker signals across broader frequency ranges. The James Webb Space Telescope and its successors will provide unprecedented views of exoplanet atmospheres, potentially revealing biosignatures or even technosignatures in the chemical compositions of distant worlds. Advanced interferometry techniques will enable direct imaging of Earth-sized planets around nearby stars, bringing us closer to answering fundamental questions about the prevalence of life in the universe. But perhaps the most significant development will be the maturation of our species' cosmic perspective. Each investigation of anomalous phenomena, each null result in SETI searches, and each discovery of exotic but natural objects contributes to our growing understanding of what's possible, what's probable, and what remains mysterious in the universe we inhabit. The correlation between the WOW signal and 3I atlas, whether it ultimately proves meaningful or coincidental, has already served a valuable purpose by focusing our attention on the kinds of evidence we would need to establish genuine connections between apparently separate phenomena. It has forced us to develop more rigorous statistical frameworks for evaluating cosmic coincidences, more sophisticated techniques for analyzing anomalous objects, and more careful protocols for distinguishing between natural and artificial signatures. These methodological advances will prove invaluable when we encounter future mysteries, and we can be certain that such mysteries will continue to emerge as our observational capabilities expand. The universe has a long history of surprising us with phenomena we never anticipated, from pulsars and quasars to dark matter and dark energy. Each discovery has required us to expand our conceptual frameworks and revise our understanding of physical reality. The search for extraterrestrial intelligence represents perhaps the ultimate example of this scientific adventure. Unlike other astronomical investigations that focus on understanding physical processes or mapping cosmic structures, SETI searches for phenomena that might have been deliberately created by beings with intentions, capabilities, and motivations we can only imagine. This search requires us to confront profound questions about the nature of intelligence, the likelihood of technological civilizations, and the methods by which such civilizations might choose to communicate across interstellar distances. It forces us to examine our assumptions about what alien intelligence might look like, how it might behave, and what evidence it might leave of its existence. The WOW signal and 3I atlas, regardless of their ultimate explanations, have contributed to this broader intellectual project by providing concrete examples of the kinds of anomalies we might encounter and the analytical frameworks we need to evaluate them properly. They have demonstrated both the excitement and the challenges of investigating phenomena that might represent our first contact with extraterrestrial intelligence. As we wait for the results of ongoing observations and analyses, we find ourselves in a state of productive uncertainty, aware of extraordinary possibilities while remaining grounded in scientific methodology. This balance between openness and skepticism represents one of humanity's greatest intellectual achievements, allowing us to pursue revolutionary discoveries while avoiding the pitfalls of wishful thinking and confirmation bias. The story of the WOW signal and 3I atlas ultimately transcends questions about alien intelligence or exotic comets. It represents humanity's coming of age as a cosmic civilization, our transition from passive observers of celestial phenomena to active participants in the search for our place in the universe. We are no longer content to simply catalogue what we see. We now actively seek signs of other minds among the stars. Whether we are alone in the universe remains one of the most profound questions our species has ever posed. The correlation between a mysterious radio signal and an enigmatic interstellar visitor provides no definitive answers, but it offers something equally valuable, a framework for thinking about how such answers might eventually emerge. In the months ahead, as 3i Atlas continues its journey through our solar system and our instruments continue their vigilant monitoring, we carry with us the accumulated wisdom of generations of astronomers who dared to look up at the night sky and wonder what might be looking back. Their curiosity has become our inheritance. Their questions have become our quest. The next wow moment may come tomorrow, next year, or decades from now. It might arrive as a radio signal, an optical flash, or a visitor from the stars displaying characteristics that leave no doubt about its artificial origin. When it comes, and the optimist in every scientist believes it will come, we will be ready. We have built the instruments, developed the protocols, and cultivated the intellectual frameworks necessary to recognize, verify, and respond to evidence of extraterrestrial intelligence. More importantly, we have maintained the sense of wonder and possibility that drives all great discoveries. The universe is vast, ancient, and filled with more stars than there are grains of sand on Earth. Among those countless suns, the laws of physics and chemistry have had billions of years to create complexity, diversity, and perhaps intelligence we can barely imagine. The correlation between the WOW signal and 3i Atlas reminds us that in such a universe anything is possible, and the most extraordinary possibilities might be the ones worth pursuing most seriously. As we close this chapter of cosmic investigation, we do so not with answers but with better questions, not with certainty, but with improved methods for pursuing uncertainty, not with conclusions but with the confidence that our species has the tools and the determination to continue seeking truth among the stars. The cosmos keeps its secrets well, but we have proven ourselves persistent students. Whether we are alone or accompanied in this vast expanse of space and time, the search itself ennobles us, challenges us, and connects us to something larger than our individual selves or our planetary home. In the end, that may be the greatest discovery of all, that we are capable of asking such questions, and brave enough to seek their answers, wherever they might lead us in the infinite darkness between the stars.